Hi everyone. In this video we're going to be introducing the Pythagorean Theorem. So we've shifted gears from algebra and we're now going to get into some geometry. At this point you should have viewed the water proof for the Pythagorean Theorem, just a short video clip. If you haven't watched that yet, pause this video and go and take a look at that video. It should be posted for you in Google Classroom. And once you've watched that video, again, it's very short, then you can pop back into this one. All right, so I'm going to assume that you've watched the waterproof for the Pythagorean Theorem. And what that demo showed was a right triangle. So a triangle is a shape that has three sides, looks sort of like this. And what this specific triangle was a right triangle, meaning that it has a 90-degree angle in it. So this, in this water demo that you just watched, this waterproof, you had a right triangle like this, and then you had these boxes coming off of it. Oh, that's poor drawing. Let's see if I can. So they were perfect squares, which my shapes are not going to be perfect squares. I'm doing the best I can here. But you had these boxes coming off. And essentially, if we were to label the length of this line on the triangle as A, and the length of this line on the triangle as B, and the length of this line on the triangle as C, what we've done is we've made three squares that are essentially each side of the triangle multiplied by itself to find the area. So if this line here is A and this is a square, that means this line is A. If this line is B and this is a square, that means this line is B. And if this line is C and this is a square, that means this line is C. And we know that we can find the area of any square or any rectangle as length times width. In this case, our length and width are the same because this is a square. And so we have A times A, right? A multiplied by A would give us the area of this square here. B multiplied by B would give us the area of the square over here. And C multiplied by C would give us the area of this square over here. Now, another way that we could say a number multiplied by itself is using exponents. In this case, A times A, we could say is A squared. B times B, we could say is B squared. And C times C, we could say is C squared. And the reason that we use an exponent of 2, the reason that we call that squared, is because using an exponent of 2, multiplying something by itself, is the way that you find the area of a square, side length squared. And so we call that exponent of 2, the special name for it is a square. So what this water demo shows is this, let me change colors here. So this square is filled with water, and the area of that square would be A squared. And this square here is filled with water, and the area of that square would be B squared. And when this apparatus here is spun, is turned, you see that all of the water drains out of this A squared and B squared square and fills into the C squared square. And it fills it perfectly to the top without any room left over. And what you see is that, or what that means then is that this square here plus this square here is equal to the area of this square here. Or in other words, a squared plus b squared is equal to the area of c squared. And this, a squared plus b squared equals c squared, is actually called the Pythagorean theorem. And it works for any right triangle. For any right triangle, remember that means that it has a 90-degree angle in it. For any right triangle, if you have side lengths A, B, and C, and A and B are connected via this right triangle, and C is the length across from the right triangle, always a squared plus b squared will be equal to c squared. And what you saw in that water demo or waterproof was somebody proving that this Pythagorean theorem, that a squared plus b squared always equals c squared, is true. You could visually see that it's true. Now, along with this video, we're going to post 2 additional proofs where people are showing that the Pythagorean theorem is true. One is a child showing the Pythagorean theorem using starburst in a clever way. And then the other one is a really good teacher, a really good math teacher, who does a great job of explaining a somewhat more complicated proof using paper and making triangles and squares out of paper. And so we're gonna link those along with this video, and you'll be able to take a look at those additional 2 proofs. And between the water demo, the starburst demo, and the paper cutting demo, you'll have seen 3 different things that prove that the Pythagorean theorem is true. So let's jump to some more space here, and we're going to define Pythagorean theorem using some specific terms. So a right triangle is like this, and it has a right angle, and we denote that with this little square in the corner. So for any right triangle with a 90-degree angle, we call the 2 lines, the 2 distances, so this distance here and this distance here, we call those legs of the triangle. So leg and leg, leg and leg here. And we can call the bottom one leg 1, and we can call this one leg 2. Or we could switch those. These are interchangeable. It doesn't matter which one you call leg 1, which one you call leg 2. It's just important that you understand that the legs of a right triangle are the 2 side lengths that make the 90-degree angle. So let's put that definition in here. The legs of a triangle are the 2 side lengths that make up the 90-degree angle in a right triangle. So that leaves one additional side of the triangle that we haven't defined yet, and that side of the triangle is the one that is across from the 90-degree angle. So you can see here's the 90-degree angle, and straight across from the 90-degree angle is the 3rd side length, which we call the hypotenuse. The hypotenuse. So the hypotenuse of a triangle is the other side length that is across from the 90-degree angle, or that is not touching the 90-degree angle. So let's put that definition up here too. The hypotenuse of a right triangle is opposite of the right angle on a right triangle. It's also the longest side of the right triangle. You can see here visually that that hypotenuse is longer than leg 1 or leg 2. Now, it doesn't matter how this right triangle is drawn. Leg 1 and leg 2 will always make up the 90-degree angle, and the hypotenuse will always be the other side that's opposite of the right angle. So even if our triangle is drawn this way, Here's our right angle. Leg 1 and leg 2, leg 1 and leg 2 always make up that right angle, and our hypotenuse will always be opposite of it. So it doesn't matter if it's drawn this way. That's a really bad attempt at a triangle. So it doesn't matter if it's drawn like this and our 90-degree angle is right here. We would then have, again, these legs are interchangeable, so leg 1, leg 2 make up that 90-degree angle, and our hypotenuse is across from it, right? Our triangle could look like this. Maybe this one's very, very short, and this one is very, very long, and here's our 90-degree angle. These legs, leg 1, leg 2, and our hypotenuse, right? Where these legs and hypotenuse are always holds true, no matter the orientation or direction of this right triangle. It's important to understand, though, that this is only referring to a right triangle. This doesn't work for all triangles. We don't call, we only call things leg 1, leg 2, and hypotenuse of a triangle when it's a right triangle, meaning it contains that 90-degree angle. So if we're looking at this in relation to the Pythagorean theorem, when we have our right triangle here, and we have leg 1 right here, and we have leg 2 right here, and we have the hypotenuse right here, we can call these two legs A and B, and we can call this hypotenuse C. And the Pythagorean theorem tells us that if we take the length of leg 1, A, and square it, meaning multiplying it by itself, A times A, and we add that to the leg length 2, which we're calling B, and you square that, so meaning B times B, that amount is equal to, or that sum is equal to, the hypotenuse C also squared. Okay? Or written out in words, we could say that the Pythagorean theorem tells us that the sum of the squares of the two legs of a right triangle are equal to the square of the length of the hypotenuse. A squared plus B squared equals C squared. Let's take a look at how we can use the Pythagorean theorem to find unknown lengths of sides of triangles. So let me make some additional space here. Whoop, I'm moving stuff that I don't want to move here. All right, so let's get some space here. I'm going to draw a right triangle. Put my 90-degree angle in. If I were to say that this side has a length of 3 units and this side has a length of 4 units, how could we find that missing side length? So we know 2 of the 3 side lengths of a right triangle, and we want to find the missing one. Well, on these, the first thing I'm going to do is I'm going to label whether these side lengths are legs or the hypotenuse. And so our 90-degree angle is right here, which makes the 3 and the 4 our leg 1 and our leg 2. So this is leg 1, this is leg 2. Again, those are interchangeable. I could have just as easily called 4 leg 1 and 3 leg 2. Or the letters that we use for those in Pythagorean theorem are A and B. So 3 is A, 4 is B. That means our hypotenuse is the question mark, C, right? This is our hypotenuse. Our hypotenuse C is the one that we're missing and we want to find. Well, we remember that the Pythagorean theorem is A squared plus B squared is equal to C squared. So we could put in For A, 3, we could put in for B, 4. And so we could say that 3 squared plus 4 squared is equal to C squared. Well, now we're going to solve this equation, 3 squared plus 4 squared equals C squared. And to do that, I need to follow order of operations. So I'm going to start out with exponents here. 3 squared means 3 times 3, right? This exponent and this exponent need to take place before we can add these values together. So 3 squared means 3 times 3. 3 times 3 is 9. So I have 9 plus 4 squared means 4 times 4, which is 16. So we can see here that 9 plus 16 is going to be equal to C squared. Now we're just going to add these two numbers together. 9 plus 16 is 25. So 25 is equal to C squared. Now we're trying to solve for C, not for C squared. So in order to undo this square, we need to do the opposite, which is the square root. If you can recall back to our study of exponents, exponential notation, we learned that the opposite of a square is a square root, basically saying what number times itself equals that number. So we can get rid of this square by taking the square root. The square root of C squared is just going to be C. But if we do something to one side of the equation, we have to do it to the other side of the equation to keep this balanced. So we can see here that C is going to be equal to the square root of 25. Well, what is the square root of 25? What number multiplied by itself equals 25? Hopefully you see that that's 5. 5 times 5 equals 25. So C must be equal to 5. So this value here, this unknown value, is 5 units. Now that was a really nice one. It worked out very easily. It gave us here in this step, it gave us a really nice easy square root to perform. Now you guys learned in your very first unit this year, you learned how to calculate irrational square roots. So we can take any value here and we can take the square root of it by hand. Remember, it's a very slow process where you're guessing checking. You find the two perfect squares that it would fall between. So let's say, for example, I'm just going to change here and go on a little side reminder. Let's say that our C squared would have been equal to 27. Well, we could take 27 and we could say which two, if we're trying to find the square root of 27, which two perfect squares is it between? Well, it's between 5 squared, 5 times 5 is 25, and 6 squared, 6 times 6 is 36. And it's closer to 5 than it is to 6, because 27 is closer to 25 than it is to 36. So then we could say, okay, it's going to be closer to 5 than 6. Let's try 5.2 times 5.2. And then we do the math. We multiply these and we do the math and we guess and check and we keep going further and further until we can get to a good approximation. So you guys know how to do this step from that first unit when we found a bunch of irrational square roots. We also learned how to use prime factorization, if you recall back, to find perfect square roots. So we could take a number like 144. If we were trying to find the square root of 144, we could make a prime factor tree, say what two numbers multiply to make 144. Well, we could say 2 times 72. 2 is prime, so I'm going to circle it. 72 is an even number. I can divide it by 2. So 72 divided by 2 gives me 36 and 2. 2 is prime. 36 can be, 6 times 6. And each of these could be 2 times 3, 2 times 3. These are all prime numbers. Once you hit prime numbers, you stop. And then I list this out as a multiplication problem from least to greatest of all my prime factors. So I have 1, 2 times another 2 times another 2 times another 2. and then times 3 and 3. And then I need to take all of these prime factors and put them into two buckets. One bucket multiplied by an identical bucket is going to be equal to 144. So I'll just separate these. I'll put a 2 here. 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 I'll put a 3 here. And I'll put a 3 here. I've used all of them, and I have two identical buckets, 2 times 2 times 3. Well, 2 times 2 is 4. 4 times 3 is 12. So 2 times 2 times 3 is 12, which means that 12 times 12 is equal to 144, or the square root of 144 equals 12. So you guys hopefully recall how we use prime factorization to find the perfect square root of a number. Or if you were to do this and get to the end here, and you couldn't fit the prime factors in two even piles, it either means that you did your prime factorization wrong. You could double check that, but it also could mean that that number isn't a perfect square, in which case we would go up and we would do this method of guess and check if you were doing it by hand. Now, the nice thing is we have calculators, and calculators can do all this tedious work for us. So when you're working on Pythagorean Theorem and you get to this step where you say, okay, c is equal to the square root of 25, just go ahead and type into your calculator the square root of 25 and let it tell you 5 if that's not one that you know off the top of your head. Or if you get to a messy one of these, like the square root of 27, just put it into your calculator, and your calculator will tell you that the square root of 27 is, let's use this approximately sign, is approximately 5.19. And it keeps going, 6152422706632. It's approximately that. So use those tools, use the calculator. There's no reason to drag these out and make them tedious if we don't need to. It's important to understand the skill of how to find a square root by hand. You guys have already shown that you can do that from our first unit. Unless you find yourself without a calculator, or you want to do this by hand, there's no reason to not use the calculator if you have access to it. Let's try another one of these. What if I had a right triangle like this? And let's say that this side length was 5 inches, and this side length was 12 inches. And we wanted to find this missing side length. Well, the first thing I'm going to do here is I'm going to locate my two legs. My two legs make up this 90-degree angle, and we call the legs A and B. So I'm going to just put an A over here and a B over here. And that means that this side here is C, which is the one that we're trying to find. And we know that the Pythagorean theorem is A squared plus B squared equals C squared. So we can just go ahead and plug in for A, 5. So 5 squared plus B, which is 12, 12 squared, is equal to C squared. Now, we're just going to follow order of operations and solve for C. 5 squared means 5 times 5, which is 25, plus 12 squared is 12 times 12, which is 144. Again, if you don't know that, you can type it into your calculator, 12 times 12, and that's going to be equal to C squared. Now we're just going to add these two numbers together. So I have 25 plus 144 is 169. You can put that into a calculator instead of doing the addition if you'd like to. And then we know that that's equal to C squared. Now we don't want to know what C squared is equal to. We want to know what C is equal to. So I'm going to take the square root to undo that squared. And if I do it to one side, I need to do it to the other. On the right here, the square root of C squared is just C. And on the left here, the square root of 169. Well, I'm just going to put that into my calculator, 169, and take the square root, and the calculator tells me that the value is 13. So we solved here for the missing side length of 13. Now, sometimes you might not get the length of both legs. So for example, what if your right triangle looked like this? What if we knew that the length of this side was 15 centimeters, and we knew that the length of this side was 17 centimeters, and we didn't know the length of this side and we were asked to find it? Well, the first thing, we're going to start this the same way. I'm just going to come through and I'm going to label these sides A, B, and C. So my legs are going to be A and B, and my legs make up this 90-degree angle. So I'll say A and B, and then my hypotenuse C is going to be across from the from the right angle diagonally. So that's this other value, A, B, and C. And you'll notice this one is different because in the previous ones we just did, we knew the value of A and B, and we were trying to find the value of C. Here we know the value of B and C, but we need to find A. Again, we're going to start this the same way. We're going to recall that the Pythagorean theorem tells us that A squared plus B squared is equal to C squared. And we're going to plug in the values that we know. We don't know A squared, so I'm just going to write A squared plus B squared. Well, we know B is 15, so I'm going to write 15 squared is equal to C squared. Well, we know C squared, we know C as well. And so I'm going to put 17 for C and squared. Now we're just going to solve for A. First thing I'm going to do is I'm going to square any of these numbers that I can. I can't square A because I don't know it, so I'm just going to rewrite A squared plus 15 squared. Well, I can do 15 squared. 15 times 15. If I put that into my calculator, it tells me that it's 225. And that's going to be equal to 17 squared. Well, I can do that too. 17 squared is just 17 times 17, which is 289. Now I'm trying to solve for A. So to solve for A, I need to get A by itself, which means I need to get rid of this plus 225 to get A by itself on the left side. So I'm going to do the opposite. I'm going to subtract 225 from each side. That cancels out, and I have A squared is equal to 289 minus 225. We could subtract those by hand here, or you could just put it into your calculator, and we get that A squared is equal to 64. Now to get A by itself, I need to take the square root because I want to get rid of that squared. The square root of A squared is just A, and the square root of 64, well, that's actually one I know off the top of my head, that's 8. You could also put it in a calculator and find that 8 times 8 equals 64. So our missing side length is 8. So you can see here that whether we have one leg and the hypotenuse or we have the length of both legs, we can always find the missing length in a right triangle, given that we know 2 of the 3 of them. Okay, let's talk about one more thing here, which is the converse of the Pythagorean theorem. So if the Pythagorean theorem, let's see if I can go back to my definition here. Oops. If the Pythagorean theorem tells us that the sum of the squares of the 2 legs of a right triangle are equal to the square of the length of the hypotenuse, then that means that A squared plus B squared equals C squared. And so we can say then that, let's go here and say if A squared plus B squared equals C squared, well then the triangle is a right triangle. That makes sense, right? If A squared plus B squared equals C squared, then the triangle is a right triangle. That's the converse of the fact that in a right triangle, a squared plus b squared equals c squared. So what that means is that we could use this definition, a squared plus b squared equals c squared, to determine if a triangle is a right triangle or not. So let's look at a couple of examples of what that means. So something is a right triangle if a squared plus b squared equals c squared. Well, what if we knew that there was a triangle that was let's get our right triangle here. So let's say that we knew there was a triangle that had a leg length of 6, a leg length of 8, and a hypotenuse length of 10. Well, if that's a right triangle, A, B, and C, let's say that we didn't have this right angle here drawn on here. Let me erase that. What if we didn't know this? Okay. And the question was, is this a right triangle? Well, if it's a right triangle, then a squared plus b squared equals c squared. Well, let's try that. A here is 6, b is 8, and c is 10. So if this is a right triangle, 6 squared plus 8 squared must equal 10 squared. 6 squared is 36, 6 times 6, right? Plus 8 squared is 64, 8 times 8, equals 10 squared, which is 10 times 10, or 100. So if this is a right triangle, then 36 plus 64 has to equal 100. Well, what is 36 plus 64? It's 100. Does 100 equal 100? Indeed it does. So since 100 equals 100, we know that a squared plus b squared does equal c squared in this case. So yes, this is a right triangle. My eyes are always tough to write here on the iPad. So yes, this is a right triangle. Let's look at another one. What if we had one like this? What if our right triangle, what if our triangle looked like this, and we knew that one side of it was 7 inches, and the other side of it was 9 inches, and the last side of it was 4 inches. And the question is this triangle a right triangle? Well, one way that we can figure that out is by testing to see if a squared plus b squared equals c squared. Well, this here looks like it could potentially be a right angle, which would make, on this triangle, our two shorter sides, right, 4 and 7, could be A and B, and we're going to see if, and our opposite line would be C. We're going to see if these values make this equation true. So A squared would be 4 squared here, plus B squared would be 7 squared, is equal to C squared, which would be 9 squared. Well, let's do this math. 4 times 4 is 16, plus 7 times 7 is 49, and then 9 times 9 is 81. Let's do this math. 16 plus 49 is equal to 65, and I have 81. 65 is equal to 81. Well, wait a second. That's not true. So a squared plus b squared does not equal c squared in this case, which means no, this is not a right triangle. Is it a triangle? Sure, it is, right? A triangle is just a shape that has 3 sides. this does have three sides. One side is 7 inches, one side is 4 inches, one side is 9 inches. It just means that this angle right here is not exactly 90 degrees. This isn't a right triangle. All right, so this is the beginning of this lesson, of this unit on Pythagorean Theorem, understanding that a squared plus b squared equals c squared, using a squared plus b squared equals c squared to find the length of a missing side, whether it's a leg or a hypotenuse, of a right triangle when you have 2 out of the 3 lengths. And then it can also be used as a test to see whether a triangle is a right triangle or not, whether that angle between the 2 legs is 90 degrees. And if a squared plus b squared does equal c squared, then yes, it is a right triangle. If a squared plus b squared does not equal c squared, well, then it's not a right triangle. All right, at this point, I'd like you to watch the other 2 demos or proofs of the Pythagorean theorem that show that in a right triangle, a squared plus b squared equals c squared. So view those 2 videos. They're fairly short. And then I'd like you to go on to your practice, which is going to be identifying missing side lengths in right triangles. And then also some more real-world application story type problems. And there's a little bit in there where you need to do some reasoning of complex shapes to use Pythagorean theorem to see if you can find missing side lengths. And some of those may be multi-step, so you may need to use Pythagorean theorem to find a missing side length in part of the shape, and then that'll give you more information that then you can apply Pythagorean theorem again to find another missing side length. As always, reach out if you have any questions, and we'll be happy to answer them, and I will see you in the next video.